My name is Solomon, and today I will walk you through getting started with your Interbotix X-Series arm. Specifically, I will focus on using the Interbotix XS-Arm Descriptions ROS package, as well as the Interbotix XS-Arm Control ROS package. So open up a terminal on your laptop by pressing Ctrl-Alt-T and typing ROS launch Interbotix XS-Arm Descriptions. XS-Arm Descriptions.launch. You can just press Tab to auto-complete that. Robot model, we're going to use the Viper X300 6-off. You can use whatever you want though. And also we're going to set use joint pub GUI is equal to true. That will just bring up a graphical user interface with some sliders that you can use to manipulate the joints in rviz. Note, you don't have to actually have the real arm connected for this. This is all happening on a virtual arm in rviz. So then press enter. And here is the rviz model in its home position. The home position is with all the joints set to 0 degrees, 0 radians. This is the joint state publisher GUI. We have all the different joints you can manipulate. Here's the waist joint. You can also manipulate the shoulder joint. So using this GUI, you can figure out pretty quickly which direction is positive rotation and which direction is negative rotation. But another way you can look at that, let's just bring up the, let's make the transparency of the robot a little bit less, something like 0.7. 0.7. Let's also turn off all these names. Actually, let's make the transparency a little bit less, 0.5. All right. So this joint over here, you can see that the TF frames for all of these joints are pretty much all oriented the same way. The Z-axis is pointing up and the X-axis is pointing straight out this way. Even for this joint over here, we see the Z-axis is pointing up and the X-axis is pointing out towards the front of the robot. And that's how all of the arms are structured. So when it comes to these three joints, the pitch joints, the shoulder, the elbow, as well as the wrist angle joint, so all of those are rotating positive, counterclockwise is positive around the y-axis. So the positive part of the y-axis. So if I get my GUI here and I rotate my shoulder in the positive direction, so using the right hand rule where you have your thumb pointing along the same axis of the positive part of the y-axis, you'll see that it's rotating counterclockwise. You can get a better view of that here. And the same holds true for the elbow joint as well as for the wrist angle joint over here. For the other joints, so for the waist joint, for example, positive rotate, you stick your thumb along the positive Z-axis and then counterclockwise from there is going to be positive. So if I rotate this positive, you can see that counterclockwise is indeed positive. And for the forearm roll joint, if in this case with the 6 degree of freedom, or for the wrist rotate joint, which is over here, so you would point your thumb along the positive X-axis and curl your hand in that direction. So if we want to do the forearm roll as positive, you can see that the rotation is indeed, counterclockwise is indeed positive. So that's how you can figure out which direction is positive for all the joints. Something else to point out, let's just center everything here. When it comes to doing IK, we can also figure out where all the, what is the planning frame. So let's disable all of those TFs and focus on the base link frame and the EE gripper link frame. Let's also show those names. So when it comes to our custom Python API that is used in all of our Python scripts, you can see in the Python demos directory, I think it's called, then it plans from the EE gripper link frame with respect to the base link frame. In Move It, it actually does from the EE gripper link frame to the world frame, and in most cases the world frame and the base link frame are exactly in the same place. So for all intents and purposes, you can think of them as working the same way. And that's that. That's pretty much it for the descriptions ROS package. There's one thing I want to point out. We're just going to run it again, but this time we're going to add show AR. I think it's show AR tag. Yeah. Is equal to true. By default, that is false. So you will note, let's focus the camera over here, that when you say show AR tag and you set it to true in the launch command, it just includes this square black piece. So if we go to the robot model and we go to the AR tag plate, you can see that with show AR tag set to false, it's not gonna have that black piece. And that's just a mount for where you can put the AprilTag sticker with the if you want to use the perception ROS package. Okay, so that's it for the descriptions ROS package. Let's Control C out of that. Now for the next part, where we're going to be controlling the arm, you want to have your arm plugged into your computer over the micro USB cable, and it also plugged into a power supply that is delivering 12 volts. And then you can type ROS launch Interbotix XS arm control.launch robot model is equal to, in this case, I'm using a Widow X200, so we're just going to set it to WX200 and press enter. So it starts out, and my robot is currently in the sleep position. So let's just look at a few things. So here is just a description of what's being loaded and all the IDs that are being found. In general, for all these arms, we start from ID 1 at the waist motor, and we just go up in number for each joint until we get to the gripper, where the gripper is the highest, has the highest ID. So in this case, the gripper is ID'd with 7. All right, so press Control Shift T in the terminal. Let's just look at a couple things. ROS topic list. The node here is publishing one topic, and that is the Widow X200 joint states. Let's just look at that one. Open up another terminal, Control Alt T, and we're going to type ROS topic echo WX200 joint states. Press enter. And you can see that in the joint state message here, all the joints are listed from increasing ID. So waist starting with the waist motor, then the shoulder, then the elbow, etc. And then for the gripper, we have the 2 finger joints as well. So the left finger, in this case, since it's positive, I put that first. And then the right finger is essentially symmetric, has the same value as the left finger, but it's negative. So that's the name. And then for the positions, that's just the positions recorded by all the present position registers in the motors are being read. And this is just the value in radians. You also get the velocity in radians per second, and the effort is in milliamps, unless you're getting, if the current is being read from the XL servos, which are in some of our arms, those aren't actually current ratings in milliamps. It is proportional to current, but it is more of, yeah, it's not the units there. It's not really current units, but it is proportional to current. Okay, so that's the joint states topic. There's also 3 topics that you can publish to. So there's the joint group topic. That is if you wanted to publish to a certain group of joints, you can do that here. The joint single topic is where you publish just one joint. And the joint trajectory topic is if you wanted to publish a joint trajectory message to a specific group of joints or an individual joint. So let's just, for the sake of it, look at that here. So we're going to, I'm just going to press Control L to clear that out. And then I'm going to type ROS topic pub -1, just want to publish one time, to the WX200 commands joint group topic. Then press tab a couple times. So the name I'm going to publish to the ARM group, because that's the only group here that we have for our Widow X200 ARM. And we're going to type 0, 0, 0, 0, and 0 again, because there's 5 different joints. It's a 5 degree of freedom ARM, and we're telling it to go to the home pose. So then make sure your arm has enough room to move, and then you can press enter. And you can see in rviz that the arm has gone to its home position. You might notice there's a bit of a sag here that is due to gravity. You can fix that by increasing the position P gain, the position P gain register, and looks like here for the elbow motor. By default, it is set to 800, I believe, but you can raise it to something like 1500, and that should make the arm have less sag. So if you type ROS, so let's just do that. So type ROS service call WX200 set motor registers, and then press tab a couple times. We're going to do single for command type, since we're only commanding this to the elbow joint. And then the name of the joint that we're commanding is the elbow. The register is called position P gain. And then the value we want to write is going to be 1500. So you might have seen there that the sag decreased a little bit, and even on the physical arm, I saw it move up a bit. So that definitely worked. Now let's command the arm to go to its sleep position. So how do you know what the sleep position is? Well, for one, you can go to the config file. So you just go, if you look here, you can go to the config directory to wx200.yaml. This is a motor config file that you can use to specify what you want the joint order to be for your joint states topic, the names of each of the joints, and then here is where we define the sleep positions for each joint. So this 0 corresponds to waist, negative 1.88 corresponds to the shoulder, and then it's the same, etc. for all the rest of the joints. So let's command the arm to go to a sleep pose. So ROS topic pub -1 Widow X200 commands joint group. Press tab a couple times. The name again is the arm group. You can actually see where we define the group name here. So here's the arm group, and inside the arm group we define the waist, shoulder, elbow, wrist angle, and wrist rotate. So essentially everything except for the gripper. Okay, so let's go here and type 0, negative 1.88, 1.5, 0.8, and then 0. And we can press enter. And if you look in rviz, our arm is now in the sleep position. So those are the ROS topics. Let's take a look at some of the services you can call. So we already used a couple of the ROS services, like the set motor registers one, but we can also look at the available services. So there's one called get robot info. Let's just check that one out quickly. Control Alt T. Let's type ROS service call WX200 get robot info, And then you can specify what you want to get robot information for. So we're going to say we want information for a certain group of motors, and we're going to get information for the arm group. Okay, so what it's going to show us is what mode is the arm group in, and right now it's in position mode. We're only commanding positions, but you could also change this to velocity or to current or to PWM or to current-based position control is one of them, I think. Profile type has to do with, it could either be a velocity or time-based. You can look a little bit more in the e-manual for Robotics to see the difference between velocity-based profile and time-based profile. Then we get the joint names for all the joints specifically in the arm group, as well as the joint IDs for the joint group. And then it's just a bunch of limit information where the index corresponds to the joint name. So the first one here corresponds to waist, the second one corresponds to the shoulder, etc. And all these values for the joint lower limits, upper limits, and velocity limits, that's all taken from the URDF. It's parsed, and those values are extracted. Sleep positions, you get that from that motor config file I showed you. Joint state indices, that's where in the joint state message you will find the states for that specific joint. So for the waist joint, it's going to be index 0 in the joint state message. For the shoulder joint is index 1. So in this case, it's all in order. And then as well, you see what the number of joints are in that group. Okay, let's type raw service list again. I'm not going to go through all of these. You can see more information about these services in the documentation. But let's just do one about the torque enable one. So let's type raw service call WX200 torque enable. Press tab a couple times. So let us torque off the arm group. So we can type group. Name is going to be arm. And enable is false. Once I press enter, all the joints for the arm group will torque off. The only one that will be left on is the gripper one. Don't press enter unless your arm is in a sleep pose or you're holding it to prevent it from collapsing. Okay, and just to show you in rviz what that would look like, once I press enter here, it'll all just collapse like that. And now you can like manually manipulate it like I'm doing right now. And then, if you wanted to position the arm manually, you can manually do that. And then when you're ready, just press up on the on your keyboard and then change false to be true like this. And then press enter like that. And now, if you want to know what the joint states are for that specific pose, you can just type ROS topic echo WX200 joint states, press enter, and you can read up what the joint positions are. Okay, a couple other things to point out. So if you go to the launch file here for the Interbotix XS arm control ROS package, you will see a few parameters or launch file arguments. There's a motor configs file. So that was something we already saw. It points to this file, which is just a bunch of, configures what the names of the joints are, the sleep positions, the groups. And then it also tells you what the default register value should be for some of the Eprom registers for all of the joints. So this is for the waist joint. This is for the shoulder joint. So you can see what the Eprom registers are. If you go to the e-manual, in this case, I'm at the e-manual for the XL430 motor, and you scroll to the control table of Eprom area. So it's all of these guys, all these registers. And I'm not setting all of them. I'm leaving a lot of them at their defaults, but a few of them I'm changing. As opposed to the control table for the RAM area, that's a whole bunch of other registers. The main difference between them is that when you power off the arm, the Eprom registers retain the values that you set to them, whereas the RAM area registers lose their values. So when you power the ARM on again, all the RAM area registers will default to whatever the defaults are that are set in the firmware, I guess. Whereas the Eprom values will retain the values that you set them previously. So that brings me to my next point here. So these are the Eprom value registers that I set. The ID and baud rate I actually don't set. That's just here for reference for what they should be. But I set all of these guys. And in general, once you set these Eprom registers, there's really no point in setting them again unless you change them in your code, which for most people, you're never really going to do. So that leads me to what the load configs parameter does. What that does is by default is set to true. It'll load all those Eprom area registers to the motors, you know, all these guys. But after running the control launch file once, you could just set that to false if you wanted to. It'll make your ARM take less time to boot up, you know, save yourself a couple seconds. Also, in general, writing, you have a limited number of times that you can write to Eprom registers before it becomes unstable. Quick Google search says about 100,000 times. So for most users, you're never going to really reach that area anyway. But that's just something to think about. You know, if you don't have to write to the Eprom registers, then there's no reason to. And then we have the mode configs file. So that's just more about the operating mode. So we can go to the config directory, go to modes.yaml. You'll see this. So this is just setting for the ARM group. We're going to set the ARM group to be in position mode as opposed to like velocity or PWM. We're going to set the profile type to be time-based profile. And then we're going to say that each move should take 2 seconds and it should spend 300 milliseconds accelerating to its max velocity and 300 milliseconds decelerating from its max velocity to 0 at the end of the move. And then torque enable is how do you want your motors for that group to be torqued on when you start the launch file or torqued off, depending on your application. Like maybe you want to write a program where you can pose the ARM in different spots manually and record the positions. You might want to set this to false. And then here's for the gripper joint. You can, for specific single motors, like if you're not just working with an ARM, maybe you're working with some robot that has a few motors on it that are just there for, you know, gripping things. You can set the operating mode to be whatever you want it, as well as what your, you can set the profile type and all these as well for the gripper. I just don't have them set here because when you're in PWM mode, profile type and velocity and acceleration don't have any effect. So it's mostly just, do you want it to be enabled by default or not? Okay, so that's it for the control ROS package. So let's just exit out of these terminals. All right, I'm going to Control C, make sure to hold the ARM so that it doesn't collapse on me. And that's it for this tutorial. Thank you for watching, and I'll see you in the next one.